Everybody, it's Mr. Gus, and I'm in my basement. I'm still home with a sick kid, but I've got some two-body systems that I wanted to show you. I've got two-body systems on an incline that I wanted to show you so we can get a chance of maybe seeing a more complicated two-body system. These are pretty challenging. I don't think they're extremely challenging, outside the realm of possibilities, but I wanted to give you a chance to look at this. So I've got two questions for you. One is just kind of thinking through some things, and then another one is going to be a deriving expressions thing. So we'll look through both. All right, right now, I've got this system, and it's on an incline, okay? And on the incline there are these two boxes. These two boxes, one is 3M, one is 2, and there are strings between them. So imagine a heavy object down here, a string attached to a lighter object, and that string is attached to this like immovable wall, okay? So we're looking at this type thing here. When we have this, my question is, what is each string doing? So before we consider this, let's do what we always do. We draw our pictures. Let's go ahead and draw the 3M model over here. Let's draw the 1M model over there. When I think about the forces acting on 3M, well, it's on Earth, so I'm going to go gravity, boom, gravity's right there, Fg. There's a normal force from the incline, so let's go up there, let's go Fn is right there. There's clearly a tension force from this thing up the incline, Ft. Now, is there friction? It doesn't really matter if there is or not. Let's just say for the instances of this case, there is some friction. So we'll say that the coefficient of friction is not equal to 0. All right? Just because we can make it as complicated as we want and understand friction shouldn't scare us. So if there is friction here, think about where these boxes would want to go, right? This string isn't pulling them up, but if the string snaps, they're going to slide down most likely. So let's say friction is probably pointed this way as well. So I have Ft, and then right on top of that, I'm going to draw another arrow and call it Ff. So I've got these two upward forces holding up the 3M mass, while gravity tries to pull it down. That's the first FBD I have right there. For the 1M mass, it should look pretty similar, except that I should have 1/3 the Fg. So I should have 1/3 the Fn. And I've got this tension force here, Ft. We call this Ft1. Let's call this Ft2 over here. Hi, Grace. Go play. And the same situation is happening here. I'll see some friction, force of friction. Now, the one thing that's different about the single mass is that there's not just gravity, normal force, and a tension force acting up and friction acting up. There's actually another tension force acting on this object, and it's this one, because the 3M, this mass, pulls down in that string. Well, if it's going to pull down in this string here is also going to pull down on the 1M mass. So we have to think about that as well. That's our third law pair, Ft1. That one there and that one there are congruent. So be thinking about that now. Now, as I think about what are these tension forces doing, what are they doing, is that they are supporting the system. Let's tackle T2 first. So let's think about T2. T2 is doing what? T2 is supporting this whole system. Let's go ahead and do our system FBD and see what that's up to. So if I have the system, I'm going to have a 4M mass with 4 times the gravity of the 1M mass, Fg. I'm going to have a normal force. I'm going to have some friction force holding it up, but also I'm going to have this whole force right here that we call Ft2. Ft2 is the only tension force that's supporting both of these masses. So consider, how big is T2 compared to T1? Well, T2 is supporting 4M worth of mass, or weight really, on an angle. It's supporting all of that. T1 is only supporting 3M's worth of mass on that angle. So if I consider which of these is larger and why, I would be thinking to myself, Ft2 is larger because it supports the entire system, the 4M system. T1 is only supporting the 3M mass. It's only supporting that in action, right? So it's only supporting 3M. T2 is supporting supporting 4M. When you think about that net force then, the net force between T2 and T1, the total of that is only going to be supporting 1M, because I got T1 pulling down, I've got T2 pulling up, and the difference between those two is just 1M. Grace, you can say hi, okay? You can say hi to the students. Say hi, students. No? Okay, fine. So this is the idea. T2 is large. T1 is smaller, and the net, the sum of T2 plus T1 is only supporting 1m worth of mass. And that's the idea here, right? So what do third law pairs do? They exist between objects like T1, and then T2 is acting on the entire system. This is the difference between FBDs on objects and FBDs on the system, okay? Let's try a different problem. Let's do an actual problem now. So I'm going to go ahead and give you this problem. If you think you're good with it, I want you to try it by yourself. Okay, so I've got a system. I've got a 4m mass. It is hung from a pulley over an incline. That's a mass of m. It's on an angle. That incline has an angle of theta. Your job is to derive an equation for acceleration. So my answer should be acceleration equals something in terms of baby g and theta. Now, you can do one of two things at this point in the video. You can go ahead and just watch me do it passively, or you could pause the video and try it for yourself and then come back, listen to my explanation, and check the answer. I think the former is the right move at this point in the unit. So pause the video, give this a try, and come back. Do you think they paused the video? You think they did? Give me a thumbs up. Thumbs up over here. Right here. Woohoo! Thumbs up. All right, we're back. Sit down. All right, now we're back. Let's go. So in order to think about this whole thing, let's do exactly what we always say we should do. Let's do our FBD. For the 4m mass, boom, 4m mass. It's got gravity on it, Fg. It's got a normal force on it, Fn. We're going to go ahead and call this thing not frictionless. There's definitely a friction force on there. So I guess this needs to be in terms of nu also. No, forget that. Not in terms of, I already told you not to. No. There we go. Okay? Now, I didn't say there was friction, so let's hopefully you assume there was no friction on this ramp. So I got Fn, I've got Fg, and then obviously there's a F tension force pulling up on the 4m mass. Let's do the 1m mass. For the 1m mass, the only forces acting on it are downward, Fg. Hopefully it's 1/4, I should make it smaller, 1/4 the size of this Fg. And then there's also an upward force on it, Ft. Now, there are two objects. Because there are two objects that are interacting with each other, I know there has to be a third law pair. So I have to identify which two objects experience the same force. Two objects, one force, Newton's third law. If I'm looking, the only force that has any relationship to each other has to be that tension force. So I would say to myself, this tension force equals that tension force. It must be true. Those two tension forces are the third law pair. So those two forces are identical. It gets a little tricky now, a little weird, when I think about doing it for the system. When I want to write my FBD for the system, this is where it gets a little bit trickier. Why? Because these two objects are accelerating in different directions. The block, the 4m block, goes this way. The 1m block goes this way. That's weird. So instead, the words I will say is, the direction of acceleration should be positive. When I go to write my FBD, the direction of acceleration should be the positive direction. So let's think about this, right? What is going to pull this object up? I have to kind of think about what forces cause this thing to move, okay? And that's going to be weird, but let's think about it. What forces cause this thing to move? Generally speaking, this thing's going to go up and over. So I'm going to go ahead and say Fg on the mass on M, just on the M block, right, on that block. That is the force that drives this motion for the entire system. The only thing driving the motion for the entire system is Fg on block M. Are there any forces, when I'm considering this, are there any forces that resist that motion? And the answer is no. There is nothing pulling back the other way. It is only this force pulling forward. Now, if there was friction, you would say, yeah, Mr. Gustin, there is some opposing force here pulling it back. But there's not. The only force that acts on the entire system moving it is the weight force, or gravity, on the 1m block. What do you think about that? You agree? Yeah, Grace agrees. Okay, so now let's go ahead and do what we always do. Let's write our F net equations. I'm only trying to find acceleration. Okay, so let's find something that I can show acceleration with. Now, let's go ahead and write my F net for 4m. All right, for F net equals 4m times A, Newton's second law. That's equal to what's pulling up? The tension force pulls up minus this parallel component of gravity, which we know to be mg sine theta. There it is for the 4m. For the 1m, F net equals m times a, and that's equal to mg, the weight force, minus that tension force. The last equation we have for the entire system would be F net equals 5m, because the entire system is both masses together. 5m times a, and that's equal to the only force causing it to move is m times g. You agree? Yeah? mg? Nice. Whose name starts with G? You do, that's right. So I've got these three equations. All you were asked to do was find the amount of force. Oh, I screwed this whole thing up, didn't I? I screwed the whole thing up, Grace. We make mistakes? And what do we say when we make mistakes? We say, get it next time. Get it next time? All right, guys, we got to back up. I forgot this. I screwed this up. Where did I screw up? If you didn't know this, that's good. But I did, in fact, screw this up. Let's go backwards. All right, here's the deal. In my system, folks, there is a resistive force. There's a resistive force right here of Fg parallel on the 4m mass. Grace, how did you let me forget that? How could I have possibly forgotten the parallel force on the ramp?
I don't know.
That's okay, let's try it again. All right, so we're back here. That's the resistive force. This gravity's pulling down. So let's try it again. I have got mg, hanging mass, minus the parallel gravity component for the 4m mass, which I already know is 4mg sine theta. Hey, Grace, you're kind of in the way. Thank you, baby. They can't see you. They can't see the board. All right. Whew. We are so back. Now, these are the correct F-net equations. Ask yourself, which of these can I solve for acceleration with? Which of these do I have known forces? Which of these do I have known variables? Two of these equations have got a force that I don't know much about, and that's this tension force. I don't know much about this tension force, so I choose not to use those equations. Could you? You could. You would have to do a lot of substitution. I'm not a big fan of that. So instead, what I'm deciding is that I'm going to go ahead and use this equation here to solve for A. All it says is that my equation needs to have A in it, and it needs to have G and theta. Yes?
I want
Give me 1 minute, okay?
I want one of the markers though.
Okay. There you go. Here's your marker. Okay? Let's go ahead and solve this. I choose this equation here. I got to isolate A. 1 second, okay? I have to isolate A. Let's go ahead and first look. These M's, boom, boom, boom. Each of those terms go away. I am left with 5A is equal to G minus 4G sine theta. Now, A is not by itself yet. I need to go ahead and say A is equal to G minus 4G sine theta over 5. Is that an equation for acceleration? Hang on 1 second, Grace. Is that an equation for acceleration in terms of G and theta? You betcha it is, right, Grace? Give me a thumbs up. Thumbs up. It matches my rules. It's an equation for acceleration. Here it is. This is a deriving equations question for a two-body system on an incline. Whew! This is a difficult question, no doubt about it, but hopefully you notice the process remains the same. You start with a picture. You draw your FBDs, you write your equations, you pick your equations, you solve your equation. The process of physics is always the same. Continue to follow that process, and even challenging questions become approachable for you. Grace, you got anything to say before I sign off? I always say this. I say, if you got any questions, you drop in the comments, you send me an email, or you ask me in class, all right? Till next time, say see ya.
See ya.
See ya.